Now we want to look at solving some problems using recursion that are a little more naturally recursive and would be much more difficult to solve with an iterative solution. So those two problems will be all permutations of the characters in a string, and we're going to print those out from that method, so that's why it's void. And then making words, meaning we will look them up in a dictionary object. In theory, this would be a very large dictionary full of lots of words. In reality, we only put 5 words in it. But for testing purposes, that'll work just fine. So we'll take the characters in a given string, and we will try to make actual words out of them, and we'll stop when we either have found a word that will work for it, or we will stop when we realize there are no words possible for it. So both of these are going to explore a large set of possibilities, and that's what recursion can be really powerful for, is checking out lots of different possibilities, or another way to think of it is making a large number of choices in a large space of possibilities for those choices. So let's take as an example the word cat. And let's say we want to define all of the possible permutations of the letters in the word cat. Well, ultimately, what we're really doing is making a choice about what letter will be the first. We could choose C as our first, we could choose A as our first, or we could choose T as our first letter. When we choose C, we have A and T remaining. When we choose A, we have C and T remaining. And when we choose T, we have C and A remaining. And so that's one of the choices, and underneath each of these choices is another set of possibilities of, well, what if I chose C? I already chose C first. What if I chose A as the next letter, leaving only T as the possible ones to choose between, leaving me with CAT as the final permutation that's possible from all of those letters. Likewise, instead, so I step back up into the reality where I have chosen C, but I still want to explore other possibilities. So what if I chose C then T, leaving only A as a possibility? That leaves C, or that creates CTA as a permutation. And then once we've done that, we actually know we've tried all of the possibilities because we know we chose C first, and all of the possibilities where we chose C first because we know we chose C first. And then we choose among either A second or T second. And we've explored all of the possibilities from that. So that takes us back up to this reality in which, now, what if instead we chose something else first? What if we chose A first? Okay. Then we have A and C as a possibility with T left over, which gives us ACT, which is in fact a word we'll see later, so that's great. But still more choices we can make. Instead of C next, we could have chosen D next, leaving C as the last possibility, ATC. And then likewise over in the other space, so once we've explored those, we know we are done with ones where A is the first choice. So now let's try T as the first choice. Okay, great, TC, leaving A, gives us TCA. And then TA, leaving C, gives us TAC. And now we can know that we have in fact explored all of the possible permutations of the letters C, A, and T. So we've got CAT as one, CAT is one, CTA is one, ACT is one, ATC, TCA, and TAC over here. Great, so now we just need code that does that. The problem is the code that, as we have it structured, only takes the letters we are going to be generating the permutations for. You can see here it just takes the string. So one thing I'm going to do, and this is always perfectly permissible, is to create a helper function for it. I'm going to call it perm. And that function, that method then, can take the string that we were originally given, but also do something like hold a result that is the permutation so far. So That allows us, users don't want to have to give us a starting result or anything like that. They just want to give us the string of letters that they want permutations for. So now I can call to my helper function, feeding it just the string that I was given, and an empty string because I know so far I have made no choices. This string will allow us to hold on to our choices so far, like we had over here on the left-hand side in our little demonstration there. So now once I'm down in my helper function, I need to think about base cases and I need to think about recursive cases. So a base case for permutations that makes sense to me is when there is nothing left at all in the string. I know that it has nothing left to do permutations for, and we saw those cases here where left-hand side had 1 character, 2 characters, 3 characters, right-hand side had 2 characters, 1 character, no characters left. And so this would be like our S, and this would be our result. And so once we have exhausted S, there's nothing left in it, we know our result is a full result. So we're going to print that result. Otherwise, we've got some work left to do. So otherwise, we actually have to go through, because you will see I went through all 3 characters, C first, A first, T first, and then once I had that narrowed down, I went through both characters, A second, T second. To do that kind of structure is to do a loop. And it's allowed to do, you're allowed to do a loop in your recursive code so long as your overall structure is still one where you are recursively calling to that method on a simpler version of the problem. Here we have to loop over it to be able to try all of those choices that are possible for us. So I is less than S length, I plus plus. So this will take us over all the characters of I. I'm going to create a character variable called choice, which is equal to the character at index I. And then I'm going to create a string called rest, which is equal to the rest of the string without that character at I. So S substring 0 to I plus S substring I plus 1 onward. So that should, in theory, give us the rest of the string, and then I have to call 2 permutations. So the string S will get replaced with rest, because it is the rest of the string so far. And then my choice needs to get tacked onto my result so far. So for instance, if I had C, and my choice was, excuse me, I called the wrong recursive function. If I had C so far in my result string and my choice now was to choose A as the second, then I need that attached on to the result so far. And in theory, this should give us all of the permutations from the letters that are given to it. Let's try it out. Okay, we can see here for the letters CAT that we came out with CAT, CTA, ACT, ATC, TCA, and TAC, all the same ones that we had in our little demonstration there. And even for something longer, like Word, we see all of the possibilities for W, all of the possibilities for O first, all of the possibilities for R first, and all of the possibilities for D first. So we can use that basic structure to solve our make word problem here. The trick is, instead of simply printing them out, we're going to use that tool called Recursive Backtracking, where what we're doing is exactly what we showed here, making a choice, trying all of the possibilities after that choice, and if those fail, we will come back and revisit that decision and instead make a different choice at that location. And we're doing it over and over. We're making a choice of C first, we're making a choice of A second, and then that forces us into a choice of T third. If that's not a new word, because we're not going to count the word that we were originally given, if that's not a new word, then we will go ahead and return to say false. We did not find a word under there, which will then return false again and come back to this case where C was our first choice and say, okay, we tried A, now try T. It's the same exact structure as our previous one. There's a couple of little differences. So first I'm going to create a helper function for this. I will call it MW. It's going to need to take a little bit extra. It needs the string S. It needs a string result. But it also needs to know the original string to avoid having itself count the word that was originally given to it. For now, I'm going to just give it a single return statement so that I can call here with S, empty string as the result so far, and S as the original, because that S was my original. We'll modify this one, just like we did up above, but we will not modify the original one. So I'm actually going to steal most of the work from the one above, and I'm going to place it in here. But where I print, I'll need to return something, and where I call to the recursive one, I need to change it a little bit, and I will need to actually use its result because it's returning true or false now to indicate to me whether I had found a word there. If I found a word, then I can stop what I'm doing, and if I did not find a word, then I will need to keep working. So if I hit the point where the length is 0, that means I have tried everything possible under this path, and there was not a word so far. So I should return false there. I checked everything, nothing there, sorry, no word. If I call down to a recursive call and it returns true, meaning that it found a word there, I don't need to keep searching. I'm done and should return true. So there is one last thing that needs to be done here, and then my structure should actually be all complete, and that is I need to actually check if the dictionary contains the word that I'm going to be building here, which is res plus choice. So the choice I made, if it builds me a word, and I'm allowing for partial words here, not just using all of the characters. I could limit it to only do it when I've run out of characters or when I only have one character left. I'm allowing it to pick up partial word or words that use only part of the letters that were given to it as well. So, same structure as before. If nothing is left in the string, I've tried everything so far, I didn't find a word, false. I return false. Otherwise, I loop across each of those characters and I make a choice. Do I pick C first, A first, T first, or C next is my other thought, because when I come down here, it's about what comes next. A next or T next. And then I'm forced into a choice in this short word situation here. If the word I was about to build, result plus choice, is a word, then I will return true. Otherwise, I will continue on by doing a recursive call using res plus choice, meaning I'll try that partial word and see if there's a bigger word that I can build with it. If there was, I return true because there is no reason to keep doing this loop through here. So again, this actually should, in theory, handle our situation for us. We have a complaint here, missing return statement, because we have the if here, the else there. So it's going to require me to put a false return in here, even though we know that this should, in theory, handle the situations because we should eventually run out of characters. We could structure it a little differently so we didn't have to put that in, but Java wants it just to be sure that we'll always hit a return statement. So now let's run through And we'll check these out. When I call for the word sword, I should get the word words. And when I call, let's do one other thing. When I find a word, let's print it so that I can actually see what it is. So now I have it printing. Let's run one more time. And we will see that when I call for sword, I should get words. When I call for cat, I should get, I think, act, or tack would also be an allowable word. And when I call for SOR, no word could be made. Great, so sword was found for words, cat was found, aha. I allowed the if orig I have to disallow the word itself from being used. If it's not equal to the original and it's in the dictionary, then we can go ahead and permit it. So now one last run through should give us sword, act, and couldn't make word. And there we have it. Words, because sword was the original, words, act, and couldn't make a word from this because there's no such word in our dictionary that matches with those. So we can see that this idea of making choices at each step allows us to explore these large spaces of possibilities, so long as we return false when we've run out of possibilities down that set of choices we made, and we didn't find the thing that we want. We return true when we did find the thing we want immediately, right now, and we return true if the recursive call gave us a true situation there because we found a solution somewhere down that sequence of choices. Like here, we found our solution somewhere under the recursive call that would have had A as a choice because it then chooses C and then chooses T and returns true at this point, passing it back up, meaning I no longer have to keep trying these other possibilities through here.